Okay, welcome everyone to this NITheCS Seminar. It's the last scheduled seminar for the year. It's possible there might be another one. We'll see if it's important terms can accommodate the person. And I'm glad to see, even though it's the last seminar, the turnout is very good. I'm not sure if that's because Peter has a reputation of being pretty good in his area. He's good speaker talker. It could be the title, or it could simply be lunch. On that note, I would point out to some people at the back that you've actually come 15 minutes too early. Yeah. Listen, I never forget things. All right, okay, fine. Glad to see everyone here. All right, so a few words about our speaker, Byron Brassel. Everyone knows him. Let's be very brief. He finished PhD at UKZN, and he then went on to join DUT. He's been there now 2 years, and he's a senior lecturer at mathematics at Durban University. Now, his interests are very broad, and general relativity, Lovelock theories of gravity, gravitational collapse, and radiating stars, not only radiating stars in general relativity, but also in Einstein-Gauss-Bonnet, apart from other interests. And he has a great love of differential equations, I think you come across in the talk today. So glad everyone is here. I'm glad to see that some computer scientists managed to find the time to come. Most welcome. And you're welcome to join us for lunch afterwards. I did ask Byron to make the talk general, because this is a broad audience. Hopefully he's done that. He's coming with a stick. I'm not sure if that's for difficult members of the audience, or he has for attendance. The
answer is attendance. Good afternoon, everyone. Thank you for coming to this, the last seminar of the year. In fact, I think my seminar was moved twice. Yeah, so I sort of prepared most of it quite some time ago, but I've been tweaking it all the way up to yesterday, just to make sure that I feel it was perfect, or as perfect as it could be. So I'm talking about a subject that's quite close to my heart now, because it's complicated, but it's also quite romantic. Not because the word love appears in the title, by the way. So yeah, the equations of gravity and what is Lovelock geometry. Okay, so because I'm quite a dramatic person, I've organized this talk in 4 acts. Okay, so the first act is where I talk about David Lovelock and what is the action of gravity. Okay, so to start off, this is David Lovelock. The only picture of him I could find. It's not a very clear picture, but he's an Englishman who was born in 1940 in Kent, in England. However, he did all of his degrees at the University of Natal, as it was formerly called. So in the late 50s, he did a BSc and his honors degree in Natal, and then completed a PhD. You would see very quickly after that, there was no master's. I don't think he's got a master's degree. He moved straight into the PhD, or he had converted. So by 1961, which would have made him 21 years old, he had a doctorate. Applied mathematics, and then he became a lecturer at the University of Bristol in England for quite a few years, and then got promoted to an associate professorship in Canada. So he moved around quite a bit before coming back to South Africa to complete the higher doctorate DSc in 1974, after which he became professor until his retirement at the University of Arizona, the USA. So he is responsible for a lot of what I'll be talking about today. Okay, so he looked like a charming person, apparently he was, but a lot of the work he did was extremely complicated. Okay, so let's start with the theory of gravity we all know and love, which is general relativity. Okay, it is the unique theory of gravity if the following conditions hold. Okay. Firstly, your space-time dimension must be greater than or equal to 3. Okay. Usually we work in 4 dimensions, but 3 dimensions is permitted under certain circumstances. we have diffeomorphism covariance or invariance. Now, this essentially means that no matter what coordinate system you work in, or wherever you are in the universe, the theories of physics are going to hold. Okay? General relativity will hold. Okay? Certain coordinate systems make your equations more difficult to work with, others easier. The point is they're all invariant under any coordinate transformation. Okay, so that's a very, very important aspect of this theory. There is metricity. Okay, so that is on the space-time manifold. You can define 2 points, take a distance between them, no matter what the curvature is. Okay, so that's a very important aspect. The equations of motion are second order. Okay, so they'll be non-linear, but they'll be at most second order equations. Okay, this is a very attractive property of GR. Okay, and finally, probably the one that is forgotten about the most is the fact that you have to have energy conservation across the entire space-time manifold. Okay, and that means that also the geometry is conserved in a sense, but I'll get to what that means a little bit later. Okay, so if you've got all of these properties, and general relativity does, it is the unique theory of gravity. Okay, so it's important to sort of know this a priori before we sort of move on. Okay, now every physical theory that we know of derives from what is known as a principle of least action. Okay, and for general relativity, the action is called the Einstein-Gauss-Bonnet action, right, which was derived independently by David Hilbert around the same time Einstein guessed his results. Okay. Einstein sort of had an aversion for mathematics, and when you do a GR course, certainly when I taught it, we pretty much showed that Einstein essentially guessed his field. Okay. It was only David Hilbert who derived the same equation from an action principle, and as I don't know if I said it, yes, the calculation is thrilling. I think every honors student should learn how to vary an action principle and get the field equation as a result. The result takes about 2.5 pages for the Einstein-Hilbert action if you write small. Okay, but essentially, any equations of motion generally have to come from an action principle. Okay, a priori. An action principle has what's called a Lagrangian within it. Okay. So for Lovelock gravity, the action principle is simply called the Lovelock action. Okay, so let's get into a little bit of what that is. Okay, so obviously it was discovered by David Lovelock, who was a student of the great Hanno Rund, a mathematician I wish I had the privilege of meeting, but I was just born too late. Right? But some members of this audience can tell you many great stories about the man. So, Lovelock gravity is an extension and a correction. Okay. In fact, a lot of people use the word extension and correction interchangeably, but it's good to use them separately. To general relativity to higher dimensions. Okay. General relativity is permitted for all dimensions greater than 3. However, I will show as we go along that Lovelock gravity allows you to add certain terms, okay, that do not ruin the dynamics or ruin the geometry or any of the conservation properties that come along with the increase of dimension. GR, as is Lovelock gravity, is a global theory, so it cannot explain everything. Case of late time expansion is just one example of one of the many aspects that general relativity cannot explain. Okay. So there's a need to modify gravity, but how you do it is important. But the nice thing about Lovelock gravity, or Lovelock geometry, is that it adheres to those points that I mentioned. Okay. All of those things still hold. Okay. And if we if we extend gravity to higher orders, order 2 is Einstein-Gauss-Bonnet gravity, which is what I work on a lot. In fact, most of my career has been working on what we call EGB gravity. Order 1 is GR. So what's very nice is that you can always get general relativity back, which is quite important. Also, as you increase the order, you pay a price. So for EGB gravity, the minimum dimension is 5 now, no longer 4. Okay. So you have one time dimension and you add an extra spatial dimension. But as I say, when the order is unity, you can always regain GR, which is very, very important. Okay. So now we can get to some of the math. Okay. The Lovelock action is written very compactly like this. Okay, where you have, I've written it in arbitrary dimensions. So the dimension of space-time is n, it's arbitrary. You have your non-degenerate pseudo-Riemannian metric. Okay. You have a space-time manifold, and you have the Levi-Civita connection. Okay. And you have the matter component. So your Lagrangian will now be the sum of all of these terms, okay, which are written in calligraphic letters there for R. Okay, so as you increase the order, you're adding terms to the original Lagrangian. So for the Einstein-Hilbert action, you will have only two terms in there, the cosmological constant, if you want it there, and the Ricci scalar. As you increase the order, you will now have quadratic terms or cubic terms, depending on how far you want to go. Okay. So it looks quite complicated. This calligraphic R is actually a product of the Riemann tensor with the generalized Kronecker delta. So just working out what it is actually quite a complicated process. Okay. And what's very important is that these coupling constants, okay, have dimensions of length. So they have to be positive. Okay. You can't have a negative alpha. Okay. So if you perform the very, very lengthy variation with respect to the metric, you'll get Lovelock's field, which look deceiving because they look rather simple, but they're not. Okay, so you have this new term here. I will explain what these are in a little bit. And on the right-hand side, you have the matter content, which we represent by T, so that's the energy and momentum tensor. You have the Einstein coupling constant, and everything on the left-hand side is the geometry of the space, okay, which as you increase the order becomes more and more complicated. But again, the equations of motion for all orders are second order. So you still have that beautiful property. Okay. And of course, if you sum to one, you'll just get the Einstein field equation. So this V becomes the Einstein tensor. Okay. So Einstein's coupling constant, in fact, changes as you increase dimension. So in 4D, it's just 8 pi, as we know. So GAB equals to 8 pi t. Okay. However, it changes according to the gamma function as you increase dimension. Okay, so the gamma function, this is the complete gamma function. So it's an integral from 0 to infinity of this particular function. So for 5b, you get 3 pi squared, and it keeps increasing powers of pi as you go along. Okay, so that has to be considered when you're working in higher dimensions. Okay. In fact, a lot of papers and results are forgotten about the increase in dimension. They've just written it as 8 pi, which is incorrect. This becomes a significantly more severe problem when you're working with electromagnetism, because the electromagnetic energy tensor depends critically on dimension as well, because it also depends on the sphere, which changes as you increase dimension. Okay, so you can also write this very nice little relation, which relates the order of the theory of Lovelock gravity with the dimension. Okay, so if in this you have it written, it's bifurcated depending on whether your dimensions even or odd. Okay, so if your space-time dimensions are 3 or 4, you stick them in there, you'll find that the maximum order of the theory must be 1. Okay, which is to say that general relativity is the only possible theory of gravity in 4D. Okay. So this is actually quite a nice little result to know. You can, I can't remember exactly how this was derived, but it's important to just know it anyway. Okay, so EGV gravity, which is the second order case, okay, it appears, okay, if done correctly, if the variation is done correctly, in the lower order limit of string theory, specifically heterotic string theory. Okay, so the action is simply what I wrote before, but where we've summed up to quadratic terms. Okay, so we have a cosmological constant, which is 0th order, and then you have the usual Ricci scalar, which is for Einstein gravity, and then you have this new term now, which is for the quadratic theory. Okay, and you've still got your matter. Now the question is, what on earth must this be, okay, for it to work? Okay, that's not an easy question to answer, but thankfully it was Cornelius Lancaster in the early 30s that came up with it, but not for this context. He was working on something else. Came up with a form, which then Zwiebak in 85 work out like this. Okay, so if you take this and you stick it in here now, and you perform the variation, it's going to tell you what those constants A, B, and C need to be, such that the field equations remain second order. So that's very, very important. It's a long calculation. Okay, that's essentially what I've just said. And I have some proof. I went off and did this myself to make sure. And there's evidence still on the floor because there's a lot of pages. It's a tedious calculation. But once you've completed it and you've done it correctly, you will end up with a full variation that looks like that. It's a bit unpleasant. The nobblers are actually the covariant derivatives. Okay. So you can see that if A is 1, B is -4, and C is 1, all the terms with fourth order derivatives are going to vanish. Okay. What I should emphasize is that the Ricci tensor, the Riemann tensor, and the scalar curvature all depend on derivatives of the metric tensor. So they're already second order. Okay, so if you're going to take two more covariant derivatives, you're going to fourth order equations. Okay? But you'll see that all of these extra little bits go away. Okay? They cancel each other out. And you are left very nicely with the single remaining entity, which is what we call the Gauss-Bonnet tensor, or the second order Lovelock tensor. Okay, it's still a very nasty piece of work to try and work out these components because we have squares of Riemann, Ricci, and scalar curvature. Okay, so it adds quite a lot of complexity to the overall field equations, and therefore, if you want the full EGB field equations, you will have. Okay, so there's the Einstein component. There is the new term that appears from the variation, which is your coupling constants and energy and momentum on the right hand side. Okay, so once you've done the full variation, you arrive at what are EGB field equations. Okay. Now, I wouldn't give the previous calculations an honor student, but it's still a very, very nice exercise in tensor analysis. So, we need to have the following, okay? We need to have conservation of energy. That's just to say that if you take a divergence energy momentum tensor, it vanishes. Okay? But also, divergence of the Einstein tensor will also vanish. Okay, that's a nice honors problem. It comes from the Bianchi identities. However, this will also vanish. If you take a divergence of second order Lovelock tensor, it will vanish too. Okay? And I'll show later that these are the only two divergence-free tensors on 5D manifold. Okay, so that's very, very important. Okay, a lot of people actually sort of forget this, neglect it. Okay, the EGB theory and all of Lovelock gravity is ghost-free. Okay, so there's no pathologies or instabilities. Okay, that is, of course, if alpha is greater than 0. If you make your alpha negative, you will have ghosts. Okay, so that's also quite important. Yes, as I mentioned before, the EGB theory is valid only when n is equal to 5 or when n is greater than 5. Okay, if you try to work out that h in 4D, it will vanish identically. Okay, another way of saying this is that the EGB theory is completely and utterly indistinguishable from GR in 4D. Okay, it is GR. Okay. So that's something to be cognizant of. Okay. And then the first of these points, and in fact the last one, also derives from Lovelock's famous theorem, okay, which brings me to Act 2. Okay. So David Lovelock is a bit of a cheeky fellow, because he proved his theorem in 1972, but he was using it all the way back in 1967 to do things. Okay, so I'm sure he just knew that that was going to happen. Okay, so the original paper was only 2 pages long. Where he talks about the four-dimensionality of space in the Einstein tensor, and he proves his famous theorem. Okay. As is the case with a lot of papers back in the day, they don't really give you much detail. You read a paper from the 70s, you have to do a lot of work. Okay. So the theorem can be stated as the following. Okay. If you consider the four-dimensional time-orientable Lorentzian manifold, that is space-time, so Lorentzian simply means that your manifold, your pseudo-Riemannian manifold, has a signature. Time orientability very simply means that the arrow of time points forward, okay, not backwards. Okay. It's endowed with your metric tensor field, pseudo-Riemannian metric tensor field. The theorem states that the only divergence-free rank 2 tensors that are constructed from the metric are the Einstein tensor and the metric tensor itself. No others exist. Okay. So any other rank 2 tensors I've written here that's naturally constructed from the metric tensor G is not necessarily divergence-free. Okay. So that is to say, very, very importantly, that if you apply it to space-time and gravity itself, the only other rank 2 tensor that is possible on the geometric side of the field equations is the Einstein tensor. No others are permitted. Okay. So it's a very interesting thing to think about. It's probably something we take for granted. Okay. But it's one thing when you're working in these theories to think about things like this. Okay. So it's literally saying the only conserved theory in 4D that describes gravity using second-order equations is GR. No others. That's what the theorem is saying. Okay. Now, I emphasize the word conserved theory. Okay. Now, this, beautifully, can be extended to 5D, where there will be an addendum. Okay. And the addendum is the following. Okay. Same thing. You've got a time-oriented manifold that is now 5-dimensional. Okay. With your pseudo-Riemannian metric tensor field, the only rank 2 tensors that are divergence-free are the Einstein tensor, the metric tensor itself, and this new tensor H that I defined earlier. Okay? No others exist. Now, another very important point, the Gauss-Bonnet tensor need not be there in 5 dimensions. You can have 5D general relativity. However, via the theorem, its admittance is allowed. Okay, so that's also quite an important thing too. Okay, and then of course, you can take it to all orders. Okay, so you take the generalized Lovelock theorem. Okay, so you take an n-dimensional manifold now, same manifold as before. It's n-dimensional. Okay, you take the order to be the lower integer part of this. Okay, n-1/2. Then the set of all of these Lovelock tensors, starting from Einstein and moving up to the kth order. Okay, will form a basis for all the real value. For the real value vector space, which is called X-love, of second-order rank 2 tensors that are, of course, naturally constructed from the metric itself, are divergence-free, and I didn't talk about this, but they're symmetric. Okay, so they are symmetric about the 2 indices. Okay. So this theorem allows one to build the entire Lovelock theory of gravity on the space-time manifold for any order that you want and for any dimension that you want to work. Okay. All right. So we can also call this a weak corollary. It's quite an interesting little observation that one can make. Okay. If you take all the divergence-free tensors other than the little metric. Okay. So excluding the metric tensor G, the number of divergence-free rank 2 tensors on the manifold is exactly equal to the Lovelock. So for EGB, we know that we have the metric tensor itself, the Einstein tensor, and the EGB tensor. So other than the metric tensor, you just have Einstein and EGB. These are the only 2, and the order of the theory is 2. And for the Einstein gravity, you will just have the Einstein tensor. So there's a very intimate relationship between dimension and order. Okay, and this is actually a very nice check. Okay. All right. So all of this is very interesting, and I constructed a nice table here. Now I put other tensors there as well. So these are just some of the curvature tensors. Not all of them. There are others that are permitted on space-time manifold depending on the dimension of the order. Okay, so you'll see in conventional VR, the minimum dimension is 3. So you'll have all of your usual tensors except Weyl, because the Weyl tensors only advantages of 3 dimensions. It only exists for dimensions 4 or more. You'll have the same tensors in EGB gravity with the addition now of EGB tensor, and so on. Pattern continues as you increase the order. Okay. So also another important point to fact is that other important points to mention is that these things sort of go up in 2s. So in EGB gravity, this tends to make a contribution in 5 and 6D, and 4 dimensions greater than that. But when you get to 7D, you are allowed another divergence-free rank 2 tensor that is now cubic in the Riemann-Ricci at scalar curvature, okay, and so on. Okay. The price you pay is that your minimum energy now increases. Okay. So it gets quite complicated quite quickly. Okay, so X3 now is like some of the applications, some of the stuff I've been working on. So with my two collaborators in front here, the famous Prof. Gauss-Bonnet and the infamous Prof. Sunil Maharaj, we've worked together for many, many years now. I think Prof. Maharaj and I, this is a decade we've been working together. So, hey, I'm not that old. I can see you. Okay, so we've written quite a few papers together, and we've done some work, as Prof. Maharaj mentioned, in gravitational collapse. So this is just a paper we published in 2022, which was a long time ago now, where we looked at cosmic censorship and the effect of charge on radiating collapse in EGB gravity, or second order Lovelock gravity. Why I put this up here is because this will still be my favorite ever referee's report, where the referee asked me to watch a YouTube video of one of his lectures, which I had to when you write the reports. Yeah, I had to say, oh, it was a good lecture. I really enjoyed it. It was insightful. Yeah, and this, of course, was extended by myself to all dimensions this year, which is, I was very proud. I was proud of the previous paper, but I was very proud of this one. A lot of work went into it. And it's the first one I've written by myself, where we talk about all of these things. We cover all the dimensions. Okay. So very quickly, all right. The charged Bulwer-Diesel metric is given by the following. Okay, so this is just a metric that's describing a particular space-time I'm working on. Okay, this is an arbitrary dimension, so your unit n-2 sphere has that nasty piece of work as a metric. Okay, so you're taking sums of the products of all the trig functions. Okay, but what's important, oh, by the way, that was first derived by David Wiltshire back in 1986. He wrote another paper about it in 1988. This gravity. This metric takes the form that is shown here. In fact, with Wiltshire's original work and Bulwer-Diesel's work the year before, they did it in n dimensions, arbitrary dimensions. Okay, so they derived it in complete generality. Okay, so it looks like this. So we've got the mass. Okay, we have Einstein-Gauss-Bonnet coupling constant. We have a charge component. We have n. Okay. Now, if you take a Taylor expansion as alpha becomes very small, you will regain n-dimensional charged Badia solution. Okay, that's a good check to do. All right. So, of course, I've just written this very neatly, so it makes this fit on the page. And of course, if I take charge away, I just get the conventional, very, very well-known Bulwer-Diesel metric. Okay, that was originally derived in 1985 with perfection. There we go, -1. There is no change in it. So what's very, very interesting, this is a point I should have made earlier, is generally in Einstein-Gauss-Bonnet gravity, your 5-dimensional case is very different and very special compared to the higher dimension case. You generally get a lot of behavior that's very unlike any dimension greater than 5. In this scenario, there's no difference. The behavior for n equals 5 and n greater than 5 is identical. This is the only example I've ever seen where that's the case. Okay, so that specialness of the 5D, dimension of 5, it's not really prevalent when you add charge. Okay, and in V2 now, we talked about this about a year ago. There's actually probably a very special reason why that is the case. Okay. Also, there's actually no space-time at r equals to 0 when you've got charge. Okay, because you'll end up with a complex result on a space-time manifold where complex numbers are not permitted because the space-time manifold is pseudo-Riemannian. It's only real numbers. Okay, I won't go into the complexities of that because it'll take too long. But take my word for it. There's no space time at r equals to 0. Okay, which is very, very interesting. But also the point Rita and I were talking about is that if you go very, very far away from the source, you can't tell the difference between the Gauss-Bonnet and the charge contributions. In fact, you can't tell the difference large distances away. And all one needs to do is take that metric function and plot it large R, and you'll see that all of them come together. You can't actually tell the difference between what is Gauss-Bonnet and what is charge. And that has probably something to do with that. Okay. When you remove charge, you take the dimension n equals to 5, the space-time is completely regular. Okay. So if you take r equals to 0, there'll be no divergences taking place, unlike in GR and unlike in higher dimensions. Okay. So the n equals to 5 collapse scenario is very, very special. However, the special diffeomorphism invariance, like the Kirchmann scalar, which is simply the squares of the curvature tensors, all diverge. Okay, which means there is a singularity in the manifold, but it's not the singularity that we think of. Okay. So this makes it sort of a quasi-regular black hole. Okay. The singularity is always initially naked for a time that depends on that coupling constant alpha. Hence another reason that alpha needs to be positive. And then the horizon will eventually form, but the singularity is no longer called a strong curvature singularity, but a weaker conical singularity. So if you think of the space-time manifold, something like this is happening. So you can fall past the event horizon and not necessarily be crushed. Okay, so it's like living in Pinetown in Donald Trump's America. You can't really escape, but you're not going to die very quickly. Okay, you're not going to have this nasty spaghettification, but also you can extend space-time through. That's another unique property. And it only happens when Q is 0 and n equals. Okay. So that's a very, very special. I can do it. Okay. All right, so this very unusual looking plot is actually not really a plot. I drew this by hand on an art program. It took me very long. Okay, this is just telling you that you have your collapsing radiation. You have an unphysical region of space because it's complex. Metric becomes complex here, so it's not allowed. So the singularity, this is what I call a branch singularity, occurs a little bit away from r equals 0. Everything collapses into it, and you do have some escaping alterations. Okay, so that's just a quick visual representation of what I'm talking about. Space-time diagrams are quite unusual. Once you get your head around what they mean, they're very useful, but they're very difficult to draw. So very quickly, just another very important result that Mirage, my infamous and famous counterpart here, worked with me on. What's interesting here is that this idea was given to me by Prof. Mirage in the end of 2014. It's a PhD project. It turned out to be quite a hard PhD project because it only got published last year. But you find that when you're doing research, you tend to find something that interests you, you move off and do a whole bunch of different things that still collates to a piece of work. So in this paper, we essentially showed that the junction conditions will hold in EGV gravity if you have an a priori result. Okay, so let's talk about very quickly what are the junction conditions. Okay, so in general relativity, in order to model a radiating star, you have to match the interior geometry to an external geometry. If it's a static star, the external is just vacuum. If not, it is the Vadia. Now, to do this, you have to do it geometrically because the outside geometry is different to the inside, and you have to match across a boundary. Okay, so you have to do some diff geometry. Okay, so the first condition is you have to match the metrics, of course, and then you have to match extrinsic curvature, which is a bit more complicated. It's got this charming little formula, okay, which depends on the normal vectors, the manifold, and of course, what are the coordinates of the surface, which we normally call sigma, as well as the coordinates of the two parent manifolds. Okay, and we showed that if they call the Israel-Damois conditions hold, then the EGV junction conditions for the matching of these two manifolds will go through and will be satisfied. Okay, so to match an EGV, you just have to show that you can match in G. These Israel-Damois conditions need. Okay. Which means that the calculation is in essence the same. Okay. So we wrote a theorem at the very end of the paper that pretty much says that we have two n-dimensional space-time manifolds that are connected by an n-1 dimensional surface hypersurface sigma, okay, the interior space-time we chose to be static as a starting point. We pretty much finished the radiating case now. Okay, we have anisotropic matter, an electromagnetic field, and we have the cosmological constant. Just try to make it as general as possible. Same thing with the exterior space-time. We have the Wilder-Wieser, Wiltshire, and de Sitter metric. Okay, so that's just the metric I showed you before, but with the cosmological constant in there. We showed that the sum of the pressures, the pressure for the Einstein part and the Gauss-Bonnet part will vanish as expected at the surface. Okay. And very nicely, you could relate, this result relates your coupling constant, your dimension, your charge, and the cosmological constant. Now, what does this look like? You write it out in full. Here's the following. Okay, I use metric potentials A and B that depend on R, so you just have derivatives of R. And you can see the effect of the cosmological constant, the charge, and there's the Gauss-Bonnet contribution. So the equation is extremely nasty, very difficult to solve in general. And then the gravitational mass is the mass of the star, takes the form that we all know and love with the additional square part. Okay, and in fact, this term here, there's a pattern that follows as you increase the order of Lovelock gravity. In effect, there's a general formula for Lovelock theories of the mass function, which I've written down. Okay, so these are just some of the things I've been working on. It's very difficult, very interesting. Okay, and there's still lots that we can do here. And this brings me to Act 4. I called my catastasis because generally it precedes a catastrophe. And this particular act is dedicated to one special person that I thought I had to give an honorary mention to. That is our foremost topologist in the room, who has, Professor Damanon Babalal, has done work, believe it or not, in Lovelock black holes. So I'm sure he'll be able to answer many questions that you have about Lovelock black holes. I put you through several papers on gravity. It's the only man I know who's front runner in topology and has published papers in the European Physical Journal C and classical and quantum gravity. I figured that required a mention. I shall with that end over here. So thank you, ladies and gentlemen, for your very kind attention and for coming.
Thank you very much for that very clear talk. You've timed it perfectly. It gives us a few minutes for discussion, questions, and then lunch. So the floor is open for questions. Gareth?
Yeah, thanks, Byron. When you spoke of second order as being one of the conditions that guarantees you that you get something or Lovelock, is that not quasi-linear second?
Yes, equations of motion are quasi-linear, so your highest derivative will be linear. But usually, what grabs you will be how non-linear those first derivative steps tend.
Sure.
Yes.
Please.
But as linear equations, why shouldn't I believe that those second order equations? What is the intuition behind thinking that equations of motion should be ordered?
That's a very good question.
Laws of motion.
They are laws. Yeah, laws of motion generally are second order.
Came from basically the Newtonian gravity area. If you know the position of particles and the velocity at a given point, then you should predict the particles at any other point. The initial conditions are the positions and its derivative. So the equations of motion are also that's how we do it.
It's in order to be able to reduce your theory to previously known theories within the context of their effectiveness.
That theory is higher order of theory, etc., you find that the effects come out, you can't tie it to observation. So you'll end up with weird effects, acostic effects, every time, depending on the ghost terms. So you pay a heavy price when you go away that part. While people are thinking of further comments, this two observations is that you emphasize this inequal part, and that's true. It comes out quite nicely. But part of the reason is in spherical symmetry, you write out the field equation. You find explicitly n-5 terms there. So you set n equal to pi, and those terms vanish. So the dynamics change. So it's not too surprising. In hindsight, one gets different geometric and dynamical features. Features coming out.
Even in GR, increased dimensions will also now have n-4 to run around as well. So 4D is a special case.
The other comment is that as you go to higher order, then you get this additional coupling constants. And this additional coupling constant for you to be a physical theory, a physical meaning. That remains a question, because you're getting these additional coupling constants, and what do they mean? So it's perhaps telling you that perhaps the only really typical ones are GR, outlining. Once you go beyond that, it's unclear.
You study it so much because of the dimension string. Yes. Orders above that, also, that form of the R squared took that particular, where scalar squared plus VG squared plus Riemann squared. The form that the R cubed term takes is not necessarily obvious. It's very tricky. And for the fourth order term, even worse. I know there are 26 terms. It's a way to work out how many terms there will be, but what they are and what they look like. Combination and take. It's very different.
Any comments?
Just a thank you. No question.
Further comments, questions? We can always interrogate him further.
Yes.
If there isn't any further, let's thank everyone.